Okay, today what we can do, we learn the SCEMATIC, right? So just start the SCEMATIC, and this SCEMATIC is a schematic tool by which you can generate your design in the schematic design, and you can do many things with the SCEMATIC, like you can make a generation of symbols and many other things which we will see later on. First of all, we design the SCEMATIC inverter design. It is already opened over here, right? So file, new, then you have to go to new design, and then whatever the design name, generally I start with ER because that is the engineer Rajesh started, right? So that is the what ER13 is there, right? New folder, whenever you want, you can go to the particular place at which you want to save from this point, 3 dots, and then you go. I am saving here on my academics drive, and the folder name I renamed it with your batch B Tech ECE, sorry, B Tech ECE, then EC4, 3 and 4 both are there, right? So 3 and 4, EC3 and 4 batch, right? So let us make it okay. Then it is went on new folder. So that is the design we have selected. Now this is the blank schematic file, so we have to go to view and go to library navigator to open this design, right? Then we go to the cell and go to the new view and see the ER3 design, and then the cell is we are designing the inverter, right? First of all, CMOS inverter, then multi-channel CMOS inverter we will design, and then we compare them both, and then we will see later on the layout if time allow. Now after this, here most important thing is whenever you have to design, you can design up to schematic or symbol or interface. So first we are designing with schematic, so we go to the schematic and then make it okay, and then there is a black sheet will come, right? This black sheet is the PCB which you can make it zoom in and zoom out, and this up to this point will be there, that there are dots, right? These are the dots in which these are the bold dots, you can call it, and here these are the 9 dots among the 10. So this zoom in and zoom out, you have to do it up to this point. After this, you will go to the library, maybe you have to add the library. So how you will add? Go to the add button from here and you add, there is a path I have already there, right? So this path is my document tenor EDA tenor tools v14.1 libraries all, and then all.tenor. This is the library path, so we have to go to that path, and after this this library has been included in this. It will come over here automatically. It is taking some time, so please bear with this, and here it is coming. Now devices, then NMOS, then instance. You have to click instance, then left. It is taking some time because it's having it. So left click is for the leaving and right click is for to leave it on this, right? So left button and then right button. In this tenor you have to do lot of things with the left and right. Now if you want to change the channel length of this, you have to go to the view window again, and then you go to the properties, and here this channel length will come, and that you can change up to 0.6 because we are using a 0.5 micrometer technology, in which 0.1 you have to allow as a lateral diffusion, right? So this will be 0.6. Now after this W is by default we are using, although it is a design parameter which you have to design by the design equations you have on the your textbooks. You can go up to that and then you can design it. But the point is, if you go to lower technology like 7 nanometer or whatsoever the things you do, then the design equation handling is a difficult task, because there are a lot of parameters involved in that, and level 54 they have gone up to. So what we do, we can design with this 0.5 micrometer, and we take the equations at the level of 1.5 micrometer, and then we take this W, we find out this W for the optimum design. After this when we done a few classes, then we find out that thing 7 nanometer file, and then we take an analysis of 7 nanometer, that is the latest, and the oldest, that is a 0.6 micrometer, which is available in the tenor by default, right? Now this NMOS is done. Now we have to pick PMOS, then instance, then we connect like this. After this we go to the wiring. Wiring is over here. This, I call it this as a dumru, right, because it is easier to recognize, right, by the student, and we call it a dumru, right? So this is the thing. We have to connect through this way. We have to start with the left mouse button, drag it over here, and then right click it to leave it. And this is the most important thing in the wiring, because the wiring is the thing which is difficult to connect over here. After this you have to connect a VDD, and before that I have to change this channel length, right? So channel length is 0.6 micrometer, and it is taking some time because C is okay, no problem. So 0.6 micrometer channel length we have done, and here W is the design parameter. So in digital circuits, always PMOS is 3 times approximately of the NMOS, and in analog circuit it is just reverse. So here we are designing a inverter design of digital, so we have to take care of this W. W of NMOS is 2.5, so W of PMOS will be 7.5. So 7.5 we have to do. So 7.5 we have done. Now after this, what we do, we take a miscellaneous. From the miscellaneous library we go to the GND and VDD. So miscellaneous, GND, take an instance and pick it over here, and then leave it. Then again you go to the VDD. You go to the VDD instance and then leave it over here, right? By left and right mouse button you can leave over here. If you want to suppose for example, if I bring this here, you can take it Control X and Control V also to bring over here. But if you want to drag this, what you have to do, you take Alt button, right, and this is used for moving any type of device or VDD or anything which you want to move. You have to use Alt button along with the left mouse button, so that you can drag it at anywhere convenient place, whichever you want. After this, this M is the multiplicity means if you are using 2, then here it will show 2, right? Or 1 and 2 and 3 and so on. Now input and output port you have to connect from this. Yeah, here it is input, here it is output, here it is bidirectional port, right? Here are some other ports that will come later on in the classes. So input you have to connect over here, and if it is not in this orientation, you just click the keyword R and you have to connect over here in this fashion. So a window will come, and then you have to rename the input, because if you are using more than one, you have to write A, B, C and so on, whatsoever you want. Then you have to write font size is 8, orientation is whatever is coming. You can change the orientation by the keyword also, and you can change the orientation from here itself also, right? So make it okay, then go to the out, then go to here, right? Then okay, then this will be the complete thing for me as far as this inverter is concerned. You can later on we will see the things in spice elements and spice commands we can also put over here, but for initialization of any software for any beginner, it should be very simple. We have to start. So this is the thing we have started. Now this asterisk show that it is not saved. So first of all we have to save it through this save design ER3. So we are saving it. So this asterisk will go, right? You can see here it is asterisk is go, and then you go to open this T-Spice to open the netlist of all the things, right? So now we are clicking this T-Spice, and then it will create automatically on the T-Spice this netlist, and then we write 5 minimum commands of every design to have a transient analysis of it. We can do noise analysis, Fourier analysis also on the T-Spice, but in here in this design what we do, we take the power analysis and the delay analysis through this T-Spice. So here it is coming. This T-Spice, you can see these are the command line which are written in green. So it is showing that on which date you have performed. That is the most important thing. And the root path it is also showing. So you don't have to worry about if somewhere it has been mess out. So you can search it very easily through this command lines, right? If you recall you have done up to this day or this fala day, you can call it through the search engine. You can find out. Now this is the netlist. It is given in the form of DGSB, right? So drain is connected to the which terminal, right? Here you can see on the copy we are showing this is the drain, this is the source, this is the body, right? This is here drain, this is will be the source, this will be the drain, and this will be the gate. Here this is the gate, this is the body, this is the body, right? So you can see everybody see, right? So here it is coming as source. If it is DGSB, right? So NMOS drain is connected to V out, right? Gate is connected to V in, right? Source is connected to GND, body is connected to GND, and same thing with here. Here in place of GND it is will be VDD, right? Gate is connected to in or V in whatsoever, and here it is V out, right? And there is a simple technique to find out from that which terminal will be source and which terminal will be drain in any CMOS. You have to follow this thing very carefully, that you put S in the ground of the lower pull down and S on the upside, and then write source drain from the upside and source drain from the downside, so that you will not mess out that which terminal is drain and which terminal is source. So that is the easier trick by which you can find out which terminal will behave like a source or drain. Now we come back to this. Here the W is we have chosen as 2.5 and 7.5, right? That is coming, and 0.6 micrometer technology was there, so it is coming over here. Along with that, it is showing area of source, perimeter